All right, everybody. Today we're going to start an exciting, weird new unit. My cat just tried to scratch my foot from behind the green screen, which is entertaining. Um, I'm sorry. I'm surrounded by animals here. I've got my dog over here, another dog, and there's a cat. And I wouldn't be surprised if there's another cat behind the other green screen here. All right, so today we're going to talk about quantum mechanics. And a wild new world. But this world is connected to the world we've been talking about, and so we're gonna walk our way there. And the cat is still clawing at my foot. What are you doing? Stop it! Gosh. All right. So a while ago we were talking about capacitors, and I mentioned that if there's no air in between two charged plates, then there's no way to get sparks from one side of it to the other. And so this is true no matter how large the voltage across the battery connecting these two plates are. You can have an electric field as large as you want, but you'll never create a conducting pathway from one side of the plate to the other if there's no air in between to be that connecting pathway. So the answer to the question of what potential difference will a capacitor in a vacuum with no dielectric produce sparks is that it's a trick question that'll never happen. So I was trying to trick you, I didn't quite succeed. All right, there is one exception to this rule. Yes, there is. And the exception to this rule, again, so we've got two charged plates connected to a battery, electric field between them. The exception to this rule is if you shine light on one of those things. And so if you shine light on one of these plates, you can potentially liberate an electron. So there's electrons on this negative plate, and it will be attracted to the positive plate. Because that's the direction, the electric field is going away from the positive, and so the electric field will suck the electrons towards the positive plate. If you try to aim this light at the positive plate, nothing will really happen in terms of current between these two plates. You'll still be liberating electrons, but they'll sort of go up, and because they're so strongly attracted to the positive plate, they'll just go back to where they started. So at the end of the day, nothing will really happen. However, there is one caveat to this, which is what this asterisk is right here, is that it depends on the properties of the light. And so in a minute we'll talk about what properties that is. Now this situation was, people were aware of it in the early 1900s, and Einstein thought a lot about this question. So even though it didn't really have anything to do with relativity, which is what he's famous for, Einstein's insight into this problem was one of his biggest achievements. So I've kind of explained it schematically. There's a very nice video that'll show you guys next, which I think does an exceptional job. So let me mute my mic and then you guys can watch that.
Here's an electroscope not so different from the one sold by Arbor Scientific. I'm going to be using it to demonstrate the photoelectric effect, which is a modern physics concept now required to be taught by teachers of AP Physics and the next generation science standards. So basically, everybody. When you charge up an electroscope, it can detect static electric charge. It helps you scope it out. There you go. The more charge you put on it, the more deflection. In this case, I'm putting negative charge on it from this balloon. There you go. And I can discharge it just by touching it. Now, I can also discharge it with light. That's the photoelectric effect. The way you do it is take a piece of metal that's sensitive to light, like zinc, and scrub it with some steel wool. This gets the oxygen layer off. Zinc oxide is not zinc, but zinc is zinc. Now we have zinc exposed to the light in the room. But the light in the room is not energetic enough to get the electricity off the zinc. So when I charge it up, I need to find some very good source of light. For example, ultraviolet light. Now I have an ultraviolet lamp right here, which I'll point at the camera and turn on, but I would never do this with your regular eyes because your regular eyes are going to be damaged easily by ultraviolet light. This is ultraviolet C, and that is the shortest wavelength of ultraviolet light that we usually use. There actually is a shorter wavelength called ultraviolet V for vacuum ultraviolet, but this one is typical. In fact, this lamp is sold as a germicidal lamp, as in it kills germs. Specifically, it destroys the DNA in the germs. Anyways, now that the scope is charged, I can discharge it with the ultraviolet light. I think that test came back positive. Now you might wonder, is it really the ultraviolet light that's doing it? In my Willemite demonstration, I showed that there's a type of ultraviolet light that's blocked by glass, that's the shortwave, which means that I can prove that it actually is the ultraviolet light if I use glass and prevent it from happening. First, I'll show that the device itself is not discharging it. Nope, nothing. Now I put the glass in front and I shine it and nothing happens. But when I remove the glass, it discharges right away. This proves that it's the ultraviolet light, the short wavelengths, that are doing it. Short wavelengths of light have a power that long wavelengths don't. They're more energetic, higher in frequency, and they have the energy required to liberate the electrons from the zinc. Now, I said electrons. What if I charged it positive? In this case, I have a fun fly stick, which doesn't produce negative charge, but positive charge. The balloon produces negative charge. When I put positive charge on the electroscope, it detects it just the same, but positive charge should not be able to be liberated by the photoelectric effect. Let's see. Come on. What's going on? Why isn't it working? Well, there's two reasons. One, the protons are stuck deep in the nucleus and they can't be removed easily except by X-rays or gamma rays or radiation from in the nucleus itself or neutrons penetrating the nucleus. Generally, you're not going to get the protons out of the nucleus. And they're also really small in there, so you're probably not going to hit them anyways. But second of all, the electrons do get knocked out easily because electrons have such low mass. I repeat the experiment again, just to show that I'm not pulling a fast one on you, with electrons that I'm gathering on this balloon. Alright. Goodbye, electrons. The photoelectric effect.
So I thought that was a nice video. Just to give a bit of context, the idea behind putting glass in between that UV light source and the zinc is that optical light can go through the glass, but UV light cannot. And so by putting the glass in front, you are finding out if optical light is enough to cause electrons to sort of jump off of that zinc plate there or not. And it doesn't work. It's only the UV part that's really doing it. I've even seen videos on the internet where they take like a conventional like desktop lamp and they put that right up to the contraption and try to see if that can get the electrons to hop off the plate because of the photoelectric effect, and it doesn't work because a conventional desktop lamp does not have super harmful UV rays emanating from it. The other lesson to be learned is that part of the reason why you should wear sunglasses is that you know, the glass in any kind of sunglasses or regular glasses can stop UV light. There's a story I heard once where one of the scientists working on the atomic bomb, everybody was supposed to wear welding goggles when they first set off the atomic bomb, but he was smart and he realized that all he needed to do was sit behind, after the initial flash, all he needed to do was sit behind a car dash, a car glass thing, what is it called? And so that was enough to stop the the UV rays, and his eyesight was fine. Anyway, so I like that demo. I think it illustrates it rather well. There is a kind of a simulation that it works in Java, which means it doesn't work on all computers. It works on my computer, so what I did is I recorded it and made a video out of it. So it looks like this. And so you have a light source here. I turned up the intensity, and now I'm shortening the wavelength from red to yellow to green to blue, and eventually I start to get to colors that actually will emit, allow electrons to be liberated from this end, and then because these two ends are at some voltage because of the battery, the electrons start to move across. But again, this only happens if the wavelength of the light source is short enough, where in a second we'll talk about what does enough mean, but there's the wavelength has to be shorter than some value for this to happen. In terms of frequency, that means that it would have to the light has to have a frequency above some value for there to be a current. So if it's above some threshold, then there's a current, but if it's below that threshold, then there's no current. And so we call this the cutoff frequency, and scientists studying this realized that the cutoff frequency is different for different kinds of metals. So this is what's called the work function. So the cutoff frequency is the work function of the metal, and so we were talking about zinc in that video. And basically the kinetic energy that the electron gets, just empirically, I'm not explaining why this has happened just yet, but the kinetic energy that the electron gets ends up being some constant times the frequency of the light minus this work function. And so what happens is that if the frequency is below this cutoff, then the kinetic energy that the electron would get would be negative, which doesn't make any sense. So the electrons will just sit there. But if the frequency is high enough, then the kinetic energy is positive, and you do get a kind of a current. So these are the work functions for the different metals there. So they were using zinc in that example. I'm not sure why they didn't use aluminum, because that would have worked just fine. But this is a table from the book, and so you could pretty easily take this and try to figure out what the cutoff frequencies are, or the cutoff wavelengths. Now, it's important to say that what they expected was this. They expected that any kind of light that was hitting that plate is carrying some amount of energy, and so enough of that light, intense enough of that light, should be able to liberate electrons and allow them to be accelerated to the other side of the plate. And so people were very, very surprised that there turned out to be a cutoff here, because if you have a ridiculously intense red light, you would think that electrons would jump from one side of the plate and go to the other one, but it doesn't. And that was a big puzzle. Why doesn't very, very intense red light do the same thing that moderately intense blue light and UV light is able to do? So the explanation for this, so Einstein was the one that came up with the correct explanation of this, and they're calling it the photoelectric effect because as we'll talk about. What's happening is that electrons are absorbing energy from the light in chunks, and so these electrons absorbed one chunk of energy from the light. And that chunk is energetic enough to liberate the electron from the surface. These electrons also absorb one chunk of energy, but that energy is not enough for it to be able to leave the surface. So the work function of that metal keeps the electrons there. And so the key thing is, and the reason that there's this threshold is that the chunks of light that the electrons can absorb have more energy, whereas over here they have less energy. Now you and I know that these chunks of energy are just photons, right? And so I've been saying chunks, but really I've meant photons. But Einstein, even though there was all this evidence that light was a wave, Einstein had the imagination to say, well, maybe it acts like a particle too. And so that's the interesting thing about this is that it's not, this picture is not a wave picture, it's more of a particle picture of light. It's a very particle-like thing for light to be doing. So there are experiments that show that light has kind of particle-like properties, and then there's other experiments that we've talked about in previous lectures that show that light has wave-like qualities. And so which is it? Is it a particle? Is it a wave? Is it a wave pretending to be a particle? Is it a particle pretending to be a wave? Is it something like that? And the answer is that it's not so simple. So for example, for me, it is easier for me to imagine that light is a wave that is pretending to be a particle, because for the shorter wavelengths, that little packet of light is going to be smaller, and so for short enough wavelength, it is more easy for me to imagine that what we call a particle of light is really sort of a very compact wave of light. But Einstein convincingly argued that that is an incomplete picture, because waves, if this really was a wave that was pretending to be a particle, waves cannot just be absorbed and destroyed. So for example, my parents are from Ohio, but I grew up in Florida, and if there was a tidal wave that was heading towards my hometown, the town would call me up, I'd talk to the mayor, and the mayor would say, what can we do to destroy this tidal wave? And I would have to say that, well, it's a wave, you can't just make it disappear or destroy it. You can try to damp it out, you can try to absorb some of that energy, but you're never going to be able to just make it disappear. Yet that is what light does. Light can be absorbed into things, especially electrons. And so if light was a particle, if light was a wave pretending to be a particle, it wouldn't just be able to be absorbed like that, is sort of the best answer that I can give. So light has to have both the qualities of waves and the qualities of particles, and it's not one or the other, it has to be both. So I think I just said a lot of these things in words. Einstein won the Nobel Prize for this. By the way, this is back in the way back when. The whole phenomena of smiling in pictures is actually relatively modern. So way back in the day, people didn't necessarily smile in photos, but this is a particularly memorable one. And so when Einstein won the Nobel Prize in 1921, they won it for the photoelectric effect, and the little note that they wrote to inform him that he had won the Nobel Prize said that you have won it for the photoelectric effect, but don't kid yourself that you've won it for relativity as well, because in 1921, Einstein's theory of relativity was still relatively untested. And so the Nobel Committee did not want to reward him for something that science had not yet fully verified. So why didn't Einstein win a second Nobel Prize for relativity? Well, after a certain point, Einstein was so famous that he was on the committee to decide who gets the Nobel Prize. It was sort of rude to, suggest yourself. He was a very modest man. So Einstein certainly deserved another Nobel Prize for relativity, but he was never awarded it. I think he was famous enough. I think he's doing okay. He doesn't need a second one, in my opinion. The energy of one photon is this. So it's the frequency of that photon times this very, very small constant. So the energy in one photon is remarkably, remarkably small, 10 to the minus 34 times whatever frequency you've got. Typically, we'll list this in hertz and this in joules. But sometimes there's other ways to write this equation that we'll do. So for example, this is another way of writing this constant. This is called Planck's constant. So pronunciation guide. This is a German last name. I've heard, so this is a German last name. The American way of saying this is Planck, like I say it, Planck. I have heard German physicists in America say Planck, but I have heard French physicists who are clearly not German say Planck. So I don't care what you pronounce it as. My advisor pronounces it Planck, because although he is American, he spent a lot of time in Paris, my PhD advisor. Anyway, so here's Planck's constant in another unit. And in these units, it allows us to continue using Hertz here, but it gives us energy in EV, and maybe this is a more helpful thing for certain problems. A third and equivalent way of writing this thing is in terms of wavelength. So let's say that we have one photon that is 800 nanometers in wavelength. This is an interesting number for me because this is the wavelength that the ridiculously intense laser at Wright-Patterson Air Force Base operates at. And so that's the energy of one photon, but if we have the wavelength, we want to know what that energy is. And so we can solve for the frequency using this, right? So C over lambda gives us the frequency, so I can write it like that. And we know what Planck's constant is, and it turns out that if you multiply Planck's constant times the speed of light, Planck's constant is a very small number, right? But the speed of light is a very large number. And then there are a lot of nanometers in 1 meter. And so if you work it all out, you end up with 1240 EV nanometers here. And so that's nice because if you have wavelength in nanometers, which is typically what we do for optical spectrum, this is not quite, this is right at the edge of one's vision, by the way, 800 nanometers. But people would say this is near IR. But so you have 800 nanometers on the bottom here, 1240. It's a very simple calculation. 1240 divided by 800 gives you 1.55. So that's the number of EV and energy that one photon of 800 nanometers would give you. Forgive me if this is pedantic, but the energy of multiple photons would be some number of photons times the energy of each photon, which is not so impressive until you realize that if you want to know the power, well then that's the energy of photons per second. You can sort of do this and you say, well, there's some number of photons per second being emitted times the energy of each photon. That gives you the power. So maybe that's helpful for some problems. All right, let's talk about quantum mechanics. So we talked a lot about light, and we talked about how if you aim light at something like this, that if light were purely a particle, then it would just make these outlines of these openings on the far wall. But it turns out that light is not 100% particle, let's say. And so you get a much more interesting pattern here. So you get a very different pattern than if you shoot machine gun bullets through there. Machine gun bullets just make the outline of these windows every time, right? And so if we shoot electrons through here, the question is, does it just trace out the outlines of this like bullets? Or does it do more or less, does it do some sort of wavy thing like the light did? Or maybe it does something different entirely. The answer is that it does sort of a wavy thing. And it's hard to explain exactly the kind of wavy thing that it does because it's not light. So electrons have a particle nature, and so I can't just show you, here's what happens when here's what happens at the far wall when I shoot electrons through like I can with a laser beam. So electrons are going to arrive one by one, basically. So it's going to look something like this, where you're going to shoot electrons through, and then if you're detecting it over here, this sort of pattern would build up. And I hope you can tell that this pattern is very different than just showing the outlines of these openings. And so there is some sort of wave-like thing going on. And this is a very strange, very unanticipated result. Very puzzling result that is sort of one of the craziest parts of physics for sure. And what is weird about it, one of the weirdest things about it is that you might wonder that, well, if I just shoot the electrons through it one at a time, maybe then they just act like bullets. And so if I just shoot them through one at a time, they'll just make a nice little outline of these little openings. But it turns out that it still does exactly the same thing, which is super weird. Because if you shoot one electron per year, there's no way for that electron to interact with other electrons as it's going through, which means that that electron is producing a wave pattern not because it's interacting with the other electrons, because it's interacting with itself somehow. And so it's absolutely bizarre, because it seems to imply that electrons are going through both of those openings somehow, because that's the only way that you can get those zeros, is if you have it's as if you have like an electron source at both of those things, and then the paths, those wavelengths sort of destructively interfere, and so you don't get any electrons in certain spots, and you do get electrons at other spots. So it's one of the weirdest things in physics for sure, but this is exactly what it does, and it doesn't matter how long you wait. This is what it's going to do. So we can ask the same question about electrons that we were with light just a moment ago. So with light, I was saying, well, is light a wave that is pretending to be a particle? Is it a particle that's pretending to be a wave? Ask the same question with electrons. So is an electron a particle that has some sort of wave-like qualities, or is it essentially a wave that is somehow behaving like a particle? And we have to give the same sort of answer, because there are situations in which electrons behave like particles. The photoelectric effect is a perfect example. An electron absorbs a photon and can jump out of that metal and start a current. So that's a very particle-like thing to do. I think for me, one of the best reminders of the wave-like nature of the electron, besides the experiment I just talked about, is the question of why doesn't the electron just fall into the nucleus? So you have this positively charged nucleus, you've got electrons, and the classical picture is that the electrons are like orbiting around the nucleus. Well, that's fine, but when I go over to a table and I knock on the table, why don't I displace enough, at least one electron that would actually spiral into the nucleus? Because if you take the charge of the electron and you take Coulomb's law seriously, so you've got 1.6 times 10 to the minus 19 coulombs in the electron, you got 1.6 times 10 to the minus 19 coulombs in the proton. You multiply those two things together, you get multiply those two things together in the Coulomb force, and they might be separated by like a nanometer or half a nanometer or something like that. That force is not much, but F equals ma, and so if you divide that force by the mass of the electron, which is 10 to the minus 31, then you get this huge acceleration. It's incredible acceleration. And you know, in the classical picture of electrons like orbiting the atom, much like planets orbit the sun, like that's what this diagram is emphasizing. It's saying that, well, Coulomb's law goes as 1 over r squared, gravity goes as 1 over r squared, so the first picture that we can have of the atom is sort of like electrons or planets orbiting some star. Well, you know what? Sometimes things fall into the frickin' sun. Like every year, there are comets. There are tiny little comets that fall into the sun. There's nothing magical that prevents any of the planets from not falling in the sun. There's people that have done their PhD theses on the possibility that eventually Mercury will get ejected and might fall into the sun, which is a long story, but it's true. So there's nothing special about gravitational dynamics that prevents the planets from falling into the sun. So why don't the electrons ever fall into the nucleus? And the answer is that the electrons never fall into the nucleus because they're waves. And so the electrons never fall into the nucleus because they're waves, and one of the properties of waves is that you cannot shrink them down to, you know, essentially infinitely small size. At some point, when you try to cram the electron into a small enough area, the electron says, hey, I'm a wave. I can't be this small. And so it is the wave nature of the electron that is the only reason why atoms are stable at all. It's kind of fascinating. So there's a lot of people out there that would say that this picture of the atom is incorrect, and that if you look at real atoms, they don't look anything like this. So for example, these are pictures of electrons in various orbitals, and the different orbitals have different energies. But when you look at this, you should not think of orbits necessarily. What you should think of as it's basically like sound waves trapped by the attractive nature of this nucleus. So in this course, we have these long tubes that have all these resonances in them. So you can think of those as like sound waves trapped inside of this sort of plastic tube. Well, this is kind of, it's almost like a sound wave trapped by a nucleus, except for instead of a sound wave, it's like an electron wave. But again, it's stuck there because the electrons are attracted to the nucleus. So in this class, we're not going to get into orbital structure. The only thing that I do need you to be able to be familiar with is the energy level N. So there's various other numbers. There's L and M. So you can leave that for a chemistry class. I don't so much care about what the orbital angular momentum number is or the spin, but I do. But what does matter to me is the energy levels. There's different levels, energy levels in an atom. So the first atom to talk about is, of course, hydrogen, which is 1 proton and 1 electron, because that's the simplest atom. And if an electron is going from one energy level to another energy level, it will either emit or absorb light, and it'll do so according to this equation. So the base change is 13.6 electron volts. So this is, again, is the equation that explains it. And so you could have electron going from the ground state to the first excited state, and maybe it's absorbing a photon, maybe it's going from the first excited state down to the ground state and emitting electron. This diagram shows all of the transitions that are in the visible range. So for example, this 3 to 2 transition, which I believe is called hydrogen alpha, it's electrons that are in the third state, the third level, which is the second excited state. They drop down to the second level, and they emit a photon when they do that, and the photon happens to be red. And in a minute we can calculate what that wavelength would be. I think they're listing the wavelength here as 656 nanometers. If instead the electron is going from the fourth energy level down to the second, well, that's more energy involved, right? Because it's a larger energy jump. So it's more energy. That means that it's a higher frequency. A higher frequency is shorter wavelength, and so that's going to give us more of a bluish light, which is this line. And same thing for the 5 to 2 transition. That's going to be even closer to the purple and the violet, n equals 6. And you notice that they didn't even show us the end of the n equals 2 to n equals 1 transition, because this transition is such high energy that it's not even in the visible range. One of my great annoyances with the universe is that the most basic transition from the first excited state down to the ground state is in the X-rays, and you have to spend $1 gazillion on spectrometers to be able to see this in a classroom. So we'll have to content ourselves with seeing these transitions. But all right, so let's check this out. So the book talks about how the energy level of an electron in a hydrogen atom in this level, energy level N, is this. So this is the energy that it is at. Now you notice that there's a minus sign here, and the reason there's a minus sign is because the electron is stuck there. And so it can change energies, but at the end of the day it's still stuck in the nucleus unless you can give it more than the energy that it needs to get away. And so this is the basic equation, and if we calculate sort of the differences in energy levels, that can tell us how much energy is involved with these transitions. So this is the final energy that the electron is at. This is the initial energy. It gives us this formula. So there's a lot of, minus times a minus is a positive, things like that. So again, this is the final energy of this is the final energy of the electron, and this is the initial energy of the electron. So if this is, so let's do an example here. So if we are emitting a photon, well, then the electron is going to be losing energy because we're emitting that photon. And so delta E is going to be less than 0. So if we're emitting a photon, we're going from a high energy state. So initially we have a high energy state, and we're going down to a lower energy state. And so that means that n sub I, our initial state, is larger than our final energy state. And so, so imagine that this is like 2, so 1 over 4. Yeah, imagine this is like 2, so 1 over 4 minus 1 over 1. So that gives us minus 3/4 times 13.6. And so if our electron is going from the second level to the first, it's losing 10.2 eV of energy, but energy is conserved, and this is the energy of the photon that gets emitted. And sure enough, if you convert this to frequency and wavelength, you will find a photon of that frequency and wavelength when you go to look to detect it. So again, this is photon emission. So there you go. We can also think about photon absorption. So in photon absorption, the electron starts at a low energy level, it absorbs a photon, and it goes up some number of energy levels. So we're going to start low. So the initial level, let's say, is 1. And then we're going to go up to the second level, let's say. So now 1 over 1 is 1. 1 over 2 squared is a fourth. And so the electron in absorbing this photon is gaining 10.2 eV. And then it uses that to go up to the second energy state. And then, of course, that energy ultimately comes from the absorbed photon. I said this before, that this energy level n is not the only quantum number. So for those of you who are in the know or study chemistry, you know that there's all kinds of quantum numbers. The next one to talk about would have been angular momentum, L. But I don't care what L is. I only care what n is, because n is what is the main thing that determines the energy of these spectral lines. So don't worry about that for the final or anything. This equation is in the book, and so you might wonder, okay, that's very interesting, Chris. For hydrogen, you know, you may be aware that there's other elements besides hydrogen in the universe, and that's true. And so the way that you modify this formula is you add a z squared on the top. And so everything else is all the same. And by the way, the atomic number of hydrogen is 1, so if you add a z squared, that still works for hydrogen. So everything is still the same except for the z squared. And so we may use this. This could easily be on the final or on one of the worksheets for trying to figure out, you know, what is the energy change and what kind of spectral features would you expect to see. So I will admit this is sort of buried in the book, but I think it's a very important equation, and it is going to be on the equation sheet for the final. So thanks for watching. That's what I've got for today. There is a worksheet for this activity that I can talk about briefly. So here we go. So this worksheet has to do with what's called the water window. So overall, water is transparent to optical light, and you know, with high enough energy X-rays, electromagnetic radiation can penetrate pretty well into light. So this is a plot of basically how far does light get into water based on its energy. And so for very high energy photons, like when you go to the dentist, I think it's like maybe like 5 keV or something. So that goes reasonably far into the water. Not as far into your bones, which is the point of doing it. But the problem is that it's hard to use that as a microscope, whereas optical light is pretty good as a microscope, but it can't always see through water super well. And so it turns out that there is this little area here, this little feature for kind of close to UV extreme UV light that actually travels surprisingly far into water, which makes it very interesting for seeing inside of cells. And so this transition has a lot to do with what we've been talking about in the course, and so you'll get a chance to see where that transition comes from in the group work. This is a real thing. I'm not making this up. So I hope you appreciate the worksheet for today.